Welcome to the LemnaTec Academy. With this video, we start into class 3. This class covers various topics around creating analysis code and analysis definitions. In the first part, we will have a deeper look into LemnaGrid. Each of these videos will cover one aspect of image analysis with LemnaGrid. In the second part, I will tell you how to create analysis definitions in LemnaExperiment and how data is handled in general. This includes administrative topics like backup as well. In the future, we will add a third part which explores creating analyses with Lemna 3D. In this video, we will have a deeper look at image segmentation using LemnaGrid. Let's start with the first analysis we created at the end of class 2. In this video, we will focus on the second device and its alternatives. The color threshold used here is one of the options for segmentation, but we have more. Let's add a few of them. We find most of them in the segmentation device section. The foreground color separation with distance threshold, the nearest neighbor foreground background color separation, the ML segmentation. If we have grayscale images, we may use a simple threshold. We can use certain calculations to create a grayscale image, which in turn can then be used for segmentation by threshold. One example of this is the red-green division. But first, let's have a look at our old friend, the color threshold device. We have a few more options in this device. In the last video, we used the HSV color space, but we could use others. The HLS color space is essentially a variation of the HSV color space. The brightness value is now called lightness. The value for saturation and lightness are calculated a bit different. The CIELAB and the CIELUV color spaces might be more interesting. The color representation in RGB, HSV, and HLS is fairly simple to understand. On the flip side, if you calculate differences between colors in these color spaces, the value between two similar colors might be larger than the difference between two less similar colors, at least if we judge color similarity by the human eye. The color spaces CIELAB and CIELUV intend to match the human perceptions of colors better. The differences between colors in these color spaces match the human perception more closely, but not perfect. Hence, we have two different color spaces. In LAB and LUV color space, we have a L value which represents the lightness or brightness of a color. The other two components represent color. These are a bit harder to explain. An image says more than 1,000 words, so I have prepared a few images to show you different color values for A, B, U, and V at defined brightness levels. At about 5%, at about 15%, at about 25%, at about 35%, at about 50%, at about 65%, at about 75%, at about 85%, at about 95%. You see that not all values which are technically possible for A, B, and U and V are actually used in these color spaces. The best way to use them is to color pick the required colors in the image and modify the border manually until you get the desired result. Let's try the LAB color space first. We focus here on adjusting A and B. But first, we have to reset the L component. Now we hover with the mouse over the image and see which values for A and B are found in the leaves. We found that the A value ranges from 100 to about 120 and the B value from 140 to 160. We see some segmentation, but the result is not what we expected. However, in the color charts we have just seen, we saw that the green is in the upper right corner. That means we can ignore the upper bound for A and B and set it to 256. A lot better. However, a few pixels at the stem are still missing. Let's zoom in on them. We can use the red cross in the right image to identify the pixels in the left image. We see that A has values lower than 100, maybe starting at 90. This looks quite good already. Let's check the other images. In this example, we selected for green, so all reddish parts of the plant are not selected. In the last image, we have another issue. Let's zoom in on it. We see that the values for B are a bit lower. Let's try 135. Okay, that looks good. The result is now satisfactory for all images. Let's do the same for LUV. We find that we need U values greater than 80 and V values greater than 144. The results look similar to the LAB result. So that is what you can do with different color spaces. In some situations, certain color spaces are more favorable than others. That depends on your images. Let's take a look into another familiar device, the nearest color foreground background separation. First, we have to connect and open it. Now we can select colors for the foreground and background. A darker green and a black are pre-selected for foreground and background colors respectively. If we want to segment leaves, this is often a reasonable starting point, like in this case. But we catch a bit too much of the pot, so we add another color to the background. We select background and then click on the position on the left image. We can identify these positions using the red cross on the right image. It looks like we are a bit too successful, so we need to add colors to the foreground. We make progress. But now we have selected too much pot again. We repeat this switching between foreground and background until we are satisfied. You may notice that the more colors we add, the longer the calculations take. Depending on the images, skill, and also luck, this may take quite an amount of colors to be defined. This device works by calculating the distances between each pixel and each of the selected colors. The color with the smallest distance wins, and if it's a foreground color, then the pixel is foreground, otherwise it is background. These color calculations are done in RGB color space. If you remember, the distances between colors are not that well correlated with the human perception. This device is easy to use and understand, but it has its flaws in terms of handling more complex images and speed. It is also harder to write its parameters into publications. A similar device is a foreground-background color separation with distance threshold. It has a similar icon as well. This time we define only colors for foreground or for background. In this example, for the foreground. All pixels within the proximity of the selected colors are considered foreground or background. The proximity is defined by a threshold. All pixels with a distance smaller than this threshold are considered to be in the proximity. The distance calculation is done in RGB color space again. Let's add some colors to define the foreground. Sometimes we are a bit too successful with adding colors. There are two ways of resolving this. We can either reduce the threshold or we can remove the color. This color removal works the same way in the next neighbor foreground-background separation. This device is similar to the nearest neighbor foreground-background color separation, including its advantages and disadvantages. It is easy to understand, but it can be slow, in particular if you add a lot of colors. And its parameters are difficult to document in publications. For the next two options, we get a bit more mathematical. The device we use now is the red-green division. It divides the red channel of an RGB image by its green channel and provides us with a grayscale representation of the result. Leaves are usually more green than red, hence the green channel is larger than the red channel, and therefore the output of this device is the smaller, the more green a pixel is. This is one of the few devices which have no UI on its own. But we can see its output in the input of the next device, which is a threshold device in this case. We can define a threshold, and all pixels above or below it are the foreground. But let's have a look at the values in the image first. Leaf parts seem to be darker than 180 or 190. But the result for this image is not as good as in the other devices. Maybe the formula implemented in the red-green division device is too simple. Maybe we need to take blue into account as well. We can use the RGB calculator and define a formula of our own. Let's start with G over R. the green channel divided by the red channel. This is the inverse of what we have used before. The result is all black, or isn't it? LemnaGrid interprets image data always in the following way. 0 is the lowest possible value and represented something like black, and 255 is the maximum. All values smaller or larger are displayed as if they were 0 or 255 respectively. So let's hover the mouse over the results image. And we see values mostly between 0 and 2, which are interpreted as almost black. Therefore, we must add some scaling factor to our calculations, 128 for instance. Now let's add some blue. We add green divided by blue times 125 to the formula. This means that we now prefer pixels to be more green than blue as well. This looks not bad, but the pot has too large values. Maybe we emphasize blue too much, but we can reduce the scaling factor for blue. Let's say 64. This was a bit too much. Let's try 96. This looks quite good already. With this result, we can now go into the threshold device and determine a threshold to differentiate between foreground and background. In the threshold device, we have to switch first which side of the threshold is considered foreground. Let's try a few thresholds. 200, 222, 240. This looks quite good, much better than the red-green division. By the way, in the Advanced tab, you can select an adaptive threshold, where the pixel must be larger by some amount than its surrounding, and you can select an upper and lower bound for the threshold, which gives you something like a bandpass. Please note the red-green division device can also be used to detect how withered a leaf is, but this will be not covered in this video. There is one more device worth mentioning. This is the ML segmentation device. With this device, you can take advantage of machine learning models created by yourself or by LemnaTec. In order to create your own machine learning models, you need to have the LemnaGrid Plus license. In Class 6, we will explain how to create your own machine learning models using LemnaGrid and LemnaExperiment. In this video, we will focus on existing models. This device can use different machine learning algorithms. More in a second. But first, let's have a look at the controls of this device. We have one to select the algorithm, another to select the model for this algorithm, a list of images used for training this model, and a button to rerun the model and another to rerun the training. At the moment, this device contains two algorithms. The color texture classifier will classify pixels by their color and the color of their surrounding pixels. You may think of it as an extension of the color threshold device and/or the foreground-background segmentation devices. This algorithm comes with no pre-trained models at the moment, although there's a base model for technical reasons. The other algorithm is InstantSeg, short for instant segmentation. It creates a grayscale image representing the distance transform. The brighter the pixels in the result are, the further they are away from an edge of some object. This can then be used to differentiate different objects of the same type in an image. Objects can be, for example, leaves. It must be combined with a watershed segmentation. In most cases, machine learning models require huge amounts of data, hundreds of thousands of images, or need to be trained for very specific tasks. Neither we nor you have this many images at hand. Therefore, we need to train our models for specific tasks. This means these predefined models might be only of limited use for you, as you can see here. However, models created for you with your data can work much better in your specific application. Let's use a different image as input. Here we see a couple of leaves from multiple plants in a plant tray. And we see a reasonable distance transformation. This result will be sent to the watershed segmentation device. However, although the output is only black and white and gray, technically it's an RGB image which just happens to contain only various shades of gray. Therefore, we have to convert it first. Since the image is only gray in the first place, we don't have to care on how this transformation is executed. In the watershed algorithm, we use version 2 with peaks and prominence marker detection, which gives us the best result. Unlike the other segmentation devices, this provides us with one object for each leaf rather than one object containing all leaves. So this covers the most important segmentation techniques implemented in LemnaGrid. There are a few more devices which cover special cases. Please ask us if you need them. This was one of the longest videos in the software training. The next videos will be shorter, I promise. In the next video, we will have a look into merging objects and working with more than one sample in an image. See you there.